Satellite of mass 10 m. It is moving in a orbital velocity r0 here in a circular path of radius capital R. Is it okay? Mass of planet here, and there is a meteoroid mass 10 m due to collides and gets stuck to it, perfect inelastic collision. He is asking this initial speed. This is a meteoroid. This is a meteoroid. No. Where the satellite, that 10 m is satellite here. It collide after collision. So let the speed of this after collision, let it be, say, before collision, let it be v. This v is unknown thing that has to be determined. Perfect inelastic collision occurs. After perfect inelastic collision, what will happen to this after collision? They'll get stuck. Then in what action? No, meteoroid is m. Yes, yeah, visible. I could not see properly. Meteoroid mass is m. So after collision, what happens? It will become 11 m. How do you expect this to move? How do the combine now will move here? I think this really it happens in our perpendicular is telling, no? Or diagram is given. So let's assume the diagram is given. Diagram is given. Let's assume that there's a diagram situation given. I think I'll make this as a diagram for the given question. Okay, fine. Let it collide like this. What do you expect after this? How do it will move? Let me shift here. I can write all the equations. The planet, you don't bother. It will be there only. Nothing will happen. The satellite motion, how it will be. I think we should apply conservation of linear momentum. So here also, yes, we can apply conservation of linear momentum. How the velocity of this satellite should be somewhere like this, no? It should be. The velocity of satellite should come somewhere like this, v1. Why? Because conservation of linear momentum you applied. Then with respect to that, it will make an angle theta. Then how do it will move? It's going to move in an elliptical orbit. So some rough diagram whose minimum distance from the planet is r/2.
So the initial point should be apogee, sir.
What you're saying? Okay, this is something smaller. It will become.
Yes, sir.
Yeah, okay, r/2, no? So it should be like this, huh? Yeah. r/2. Okay, now we can, and that this distance is what is telling r/2. So this should be the at foci. I think some rough diagram I am bringing it will not appear. It's not appearing good. Elliptical orbit. Okay, I think little bit now fine. And this is r by 2. So here it will have the velocity, say v2. Okay, apply now all the things, what all. So let's apply conservation of, and it will make an angle theta with this one. So let's apply conservation of linear momentum first. So what was the initial momentum along x-axis? mv is equal to final momentum 11m v1 sine theta. Theta is unknown, we assumed it. So therefore v is equal to 11 v1 sine theta. Along y-axis, initial momentum of satellite. Along y-axis, the initial momentum of satellite 10 m v naught, and final momentum 11 m v1 cos theta. So cancelling m, 10 v naught equal to 11 v1 cos theta. Okay, these are some hard equations what we have from call equation 192. Any other equations can we write? Applying conservation of angular momentum. Between what? Between the collision point and the perigee and apogee. This will become, shall we give some name? Like shall we call this as apogee? Now applied. So according to conservation of linear momentum, conservation of angular momentum about planet 11 m v1 cos theta into r should be equal to 11 m v2 r by 2. From where this is brought, conservation of angular momentum about the planet. So 11 v1 cos theta, r will get cancelled. So 11 v2 by 2. 11 also get cancelled, no? Here. This is the equation 3. Together we'll call equation 3. Any other equations shall we write? Conservation of mechanical energy. What is the mechanical energy? It will be minus g mass of planet 11m r plus 11m v1 square by 2 r by 2 plus 11m v2 square by 2. But mass of planet mp, no, that mass of planet is mp, we assumed it. In terms of that, we'll try to bring the answer. What is the orbital speed? So where all gmp is there, you can write v naught square r, so that you can bring into the picture. So this will be v naught square r equal to, so this equation. Solving all this, we'll get the required answer. So I think, say the moment elliptical orbit comes, you take it for granted. Conservation of angular, conservation of mechanical. Any collision are there, conservation of linear momentum. Conservation of linear momentum, conservation of, this is conservation of mechanical energy. See, all fundamental ideas, just the problem revolves around all the fundamental ideas. The answer 58. This is very often it happens, no? So I think these are the biggest problems what we face when we launch satellite. When we launch satellite, what is the meteorite? Here better you can say cosmic dust. So therefore, the surface of satellite weapon is so designed that the dust should not catch on it. That's why you can see like a very smooth shining it is made. The reason for that, any dust should not catch. If it catches dust, no, its momentum will change. And instead of circular orbit, it may revolve like this here. So these are some technical problems. Inelastic means what happens? The dust will catch it. Even some meteors, no? Usually most of the meteors will be hard. They come and collide. So here they just brought meteor for your understanding purpose, but practical it become a dust. The dust also will be in motion outside that one. So that dust open catches, no, it will change the course of the satellite.